Okay, so I want to prove to you the Fuglede-Putnam theorem. Which says that given A, B, and X in a C-star algebra, where A and B are normal, then if I know that AX is XB, then I also know that A star X is XB star. So this is sort of an intertwining type of equality. So that says that, you know, if the X intertwines A and B, so AX is XB, then actually X also intertwines A star and B star. And of course this is trivial if A and B are self-adjoint. So the point is that we can prove this under the much more restrictive condition that A and B are normal. So the first thing we do is that we note that A to the n times X is X times B to the n, just by using the equality n times, moving NA's to the other side of B. So by, and I'll put in parentheses, holomorphic functional calculus, we get that e to the IA x is x e to the IB. And what do I mean by e to the IA? Well, of course, e to the IZ is a function which is defined on the spectrum of A or B. So we can use, and they are normal, so we can use the continuous functional calculus. But you know, it's also a holomorphic function defined on a neighborhood of the spectrum of A and B. This is something that we did before we had the C-star algebra. So before we had the star, before being normal even made sense. So in a sense, this is what I'm using. And of course, the point is that e to the IA is, we can define it by sort of plugging into the standard power series for the exponential function. And then the point is that because we know that whenever I have a power of A to the left, that's the same as having the same power of B to the right. So I can just take all these terms and check, and then I put on an I to the n and the n factorial. So if I have a finite segment of this series, then obviously I can pull the x from one side to the other as I need, and then I will just go to the limit. Right. So the point, in a sense, is that when I'm using if I'm using the continuous functional calculus, I can approximate my function with functions that are not that are honest polynomials, right? Because if I had something with a lambda or z complex conjugate, that would actually mean that I was plugging in an A star or B star, and this is exactly what I'm trying to prove I can do, right? So at the end of the day, this is what we will prove is possible, but we're not there yet. So, but using continuous functional calculus, we get that e to the I A times e to the minus IA times e to the minus IA e to the IA is 1. So remember, this was the kind of argument in a sense, you know, I'm using that e times z plus w is e z e W. And you remember me struggling proving this in order to prove this is the first version of the proof that when I have a self-adjoint operator, the spectrum is contained in the real line. And I did this because I had to by going back to the power series and working with the Cauchy multiplication, which we showed made sense in general Banach algebra. But the point is that now that I have proved that the spectrum of a self-adjoint element is contained in the real line, and use this as a corollary to prove that that we have the continuous functional calculus, I don't need to do this anymore, right? Because I know that e to the ia is just that function e to the iz applied to a, and I know that the equation that I've written up holds with the z and not an a. Right, and then just because of the properties of properties of the functional calculus, I get the conclusion that I need. And of course, I can do the same with B. They have the same. They have the same given assumptions. So this is true. So really. Maybe a more convenient way of writing this, right? So really, what I found is the inverse e to the ia is invertible, and the inverse is e to the minus ia. So a nicer way of writing this equation is to put on an e to the ia x, e to the ia. And then x, and then e to the minus ib is the same as x. Right, so this is going to be, I'll call this dot, and this is what we're going to work with. So how about if we look at e to the ia star x e to the minus ib star? What can we say about this? Well, it is e to the ia star, e to the ia, x, e to the minus ib, e to the minus ib star, just by using, this is where I'm using the dot equation again. And the point that I'm trying to make here is that I can actually say something about the norm of the terms to the right and the left of x, because of course they have the form e to the I a star plus a, x e to the minus I b plus b star, like so, where the spectrum of e to the I, say a star plus a, for instance, we know is contained, I'm using the continuous functional calculus, but because of the spectral mapping theorem, is the same as e to the I spectrum of a star plus a, right? And the spectrum of a star plus a, since a star plus a is obviously self-adjoint, is contained in the real axis, so e to the I of that is contained in the unit circle, right? So this means, because these are normal elements, this means that the norm of e to the I of these elements are bounded by 1, right? So so I'll say similarly for B. So the norm of e to the ia star, b e to the minus ib star, is, I mean, because of the computation we just did, right? This, what I have in here is the same as what I have out here, and these normal elements have their spectra contained in the unit circle, so their spectral radius is 1, so this means that their norm is 1. So this is less than norm of x, and of course I need to write here x, not b. Okay, so note also that if I take a lambda in the complex numbers and I write lambda ax, this is the same as x, lambda conjugate ax is the same as x lambda conjugate b, right? Just because I'm multiplying on this scalar. So we get, oops, so we get that actually the norm of e to the I lambda a star x e to the minus I lambda b star is always less than the norm of x. Now, why is that? That's just because I proved this one. Let me call it triangle. Right? I proved this under the assumption that ax is xb, but we've seen that lambda bar a is also the same at times x is also the same as x lambda bar b. So I can just plug in and I can put lambda bar where I used to have the lambda bar a, where I used to have the a, and lambda bar b, where I used to have the b. Right? And because of the stars, I get rid of the conjugation, so I get this equation here. Now, by Cauchy multiplication, and we know that we can do Cauchy multiplication. This was an exercise. We can do this in any Banach algebra, in particular in a C-star algebra. All we need to know is that when we do the Cauchy multiplication, we have something which is absolutely summable. So we have to take the norms, and this should give us a series that was summable. Right, so this gives that when I look at e to the I lambda a star x e to the minus I lambda b star, I can actually write this out as a sum, right? So this is the sum from n equals 0 to infinity. I put here I a star to the n factorial, and then I put lambda to the n. Right? So it looks like a power series with the coefficients from the C-star algebra. Then I have my x, and then I do the same with the b's. So this will give me, I guess, minus I b star to the n factorial lambda n. And because I know that these two sequences converge uniformly, keep getting this word, they converge so they converge absolutely. So I can reorder my sums, right? And actually, it turns out that I only need to look at very few of the terms. So I will just take the first two terms. I have here I a star times lambda, and then I have something, doesn't matter. Then I have an x, and then I have 1 plus minus I b star lambda plus blah. And let's just collect the terms, right? So I have the term where there's no a's or b's, and then I have the term where there is exactly one a or b, right? So this gives me I a star x minus x I b star. This is times lambda, and then this keeps on going. But the point is that Liouville tells me that this expression has to be constant in lambda, right? So by Liouville, and here I'm being a little bit sloppy, let me explain in a second more carefully what I'm doing. The expression must be constant. So this means that the coefficient to lambda is 0. So I a star x must be the same as x I b star, right, which proves what we're after. But of course, there is no Liouville theorem for general sums in C-star algebras. So what we have to do, and let me just sort of sloppily put it in here, right? We have to choose a linear functional, and then we apply that, right? So we apply this everywhere, and then we will have some phi's here and here and here and so on, and then and here, and then and here and here, and so the point is that then we get number a function that attains complex numbers as its values, and we can see that this is going to be an entire function, a holomorphic function defined everywhere, which is bounded by the inequality that we established up here, right? And then because we can do this for all phi's, then by Hahn-Banach we're done in the sense that I explained before. So this proves the Fuglede-Putnam theorem, and if you feel like using it in the third assignment, in second assignment, question 3, you're very welcome.